Hi everybody, this is Mrs. T, Mrs. T's Chem Talk. This is going to be a live stream Chemistry Regents review. I am just double checking that everything is working. So just give me a couple minutes and we'll get started in a few minutes. Awesome. Okay, so it looks like everything is working. I'm going to go through a series of topics that the students that I have in my own classes submitted to me. And if at any time my students or my review students want to ask me a question, you can just send me a message on and those messages on Remind. I'll be reading them periodically to make sure that I can try to address the questions that you have that come up. Try to answer as many questions as I can throughout the live stream here. And for anyone, if you know anyone who didn't get to watch right now, you can certainly tell them that they can watch this. It will get archived on YouTube. For anybody who doesn't know who I am, I'm Mrs. T. I teach chemistry at Calhoun High School in Merrick, New York. So the first topic that we're going to go over a couple of things in is physical behavior of matter. Before we do that, I would suggest that you have out a piece of paper and a pen just to kind of jot down any questions that you may have, because you are on a slight delay, which means that I may be on to the next topic already when you decide that you have a question. Okay, so I just got a message that the mic is very echoey and it's hard to hear. See if I can fix that. I would suggest having your volume all the way up, because on my end, I did test the audio on my laptop and it's coming through fine for me. So just make sure that your volume is adjusted. And if you could just let me know if it's still echoey on your end, I'd appreciate it. So I'm going to start with some physical behavior of matter topics, but again, I would suggest that you have your reference tables out, maybe a calculator out, and also a piece of paper to make sure that you can write down some things if you want to ask me some questions. So the first topic that was submitted in physical behavior of matter was about Avogadro's hypothesis. Avogadro's hypothesis says that equal volumes of gas at the same temperature and pressure have the same number of molecules. So for example, if we have a balloon of helium, a balloon of nitrogen, and a balloon of methane, they all have different formulas, but because their volume, 22.4 liters for each of them, pressure of 1 atmosphere each, and temperature of 0 degrees Celsius each one has a different mass, but they each have the same number of molecules. They have the same number of moles of molecules and the same number of individual molecules. The next topic that was asked about was the gas relationships between temperature, pressure, and volume. Okay, so I seem to be having some volume issues. I'm going to double check on my end that I can hear it through my laptop. Let me just double check and make sure that the volume is working on my end, and then I'll get started again. Okay, so I'm still not sure why why some people are having audio issues. I am previewing the video on on another computer here, and I can hear the volume. It's not very loud, the volume. It's not as loud maybe as it would be, if you put your TV up or your volume up that high. But I am hearing volume, so I'm wondering if there's a problem. I don't know what the problem is, but the video is going through YouTube with volume on my end. I'm testing it, so maybe you want to try and watch it from a different place. Okay, so I just going to continue on with the gas relationships. And when we talk about the gas relationships, when we talk about pressure versus volume, when we increase pressure, volume is going to decrease. We call this an inverse relationship. Volume versus temperature is going to be a direct relationship, and temperature versus pressure is also a direct relationship. These these graphs also, you can remember them if we talk about pressure, temperature, and volume, and we put the letters in alphabetical order, PTV. Pressure is direct with temperature, it's directly next to it. Temperature is direct with volume, it's also directly next to it. Pressure and volume are inverse, they are not next to each other. The next question that was asked about was the heat formulas for table T and B. And I just thought of something else for the volume issue. So let me just double check and make sure that my mic volume is all the way up. Okay, so I am hoping that increased the volume. So I'm just going to ask if you could bear with me, and those of you who said that the volume was not so good. Oh, I just got a message. Okay, so the volume is better now. So I'm so glad that we fixed that. I'm sorry that you weren't maybe hearing what we did at the beginning, but hopefully from now on the volume will be good. So that volume boost seems to be working. So really glad that we were able to fix that problem. So when we talk about the heat formulas from table T and table B, if there is a problem with a temperature change, we are going to use Q equals MC delta T, because remember that delta T means temperature change. That means change in temperature. If we're talking about a phase change, when you're talking about melting or freezing, so melting, remember, is solid going to liquid. Freezing is liquid going to solid. You're going to use Q equals MHF. And if we're talking about boiling or condensing, which remember, boiling is liquid to gas, condensing is gas to liquid, we're going to use Q equals MHV. Table B has the constants on it. Remember that the C is called the specific heat, and the values for water are found on table B. HF is called the heat of fusion, and it's the amount of heat it takes for 1 gram to melt. And HV is the heat of vaporization. The heat of fusion and the heat of vaporization, again, are for phase changes. The delta T formula, the C is called the specific heat. That would be for a temperature change. Remember, when the temperature changes, we use the delta T formula. Delta T means temperature the final temperature minus the initial, just the difference between them. And for phase changes, remember that the temperature will not change at the same time. The next question that was asked about was about the heating curve and cooling curves. Remember that anytime an energy graph goes uphill, the energy change is endothermic. That means that for the heating curve, temperature is going up, so heat is being added, heat is being taken in this process. Anytime we have a slanted line on the heating curve, we have a change in kinetic energy, because remember, kinetic energy is measured by temperature. So the kinetic energy is increasing whenever the temperature is increasing. But remember that at a phase change, the temperature is not changing at all. So on the heating curve, the phase changes show an increase in potential energy. It's the potential energy that changes when the phase is changing on an endothermic or exothermic phase change, heating curve. So the heating curve is endothermic. Remember that the cooling curve would be the opposite of this, and it would be exothermic. Remember that the phase changes again. We have freezing and melting when we go from solid to liquid. We also call melting fusion. That's where that word heat of fusion comes from. For the cooling curve, gas to liquid is called condensation. But remember, vaporization, another word for vaporization is boiling. When we talk about atomic structure, that's going to be the next topic that we'll talk about. One of the questions that was asked about was about the bright line spectrum. Okay, sorry, I have a question to go back to the heating curve. It was asked about which part of the endothermic graph to potential energy and kinetic energy remain the same. So only one type of energy changes at a time. So when the kinetic energy is going up, kinetic energy is remaining the same. So when the temperature is changing, nothing's happening to the potential energy. When the potential energy is changing at the phase change, kinetic energy is remaining the same. So only one type of energy changes at a time. Potential energy changes at a phase change. Kinetic energy does not. Kinetic energy changes when the temperature is changing. Potential energy does not change there. Hopefully that answered your question. So when we talk about the bright line spectrum, remember that we have energy changes associated with electrons moving up and down levels. So remember that the electrons originally or usually exist in the ground state. The ground state is defined as the lowest energy configuration for electrons. And remember, the ground state is found on the periodic table. The excited state happens when an atom absorbs energy. When an atom absorbs energy, the electrons move up to the excited state. They move further away from the nucleus. That state is a temporary state. The electrons can't stay there. So then when the electrons move back down to the ground state, they release energy as light. The energy that's released as light can be separated into the bright line spectrum. Each element has its own unique bright line spectrum, and so we can actually identify elements present in a sample based on the bright line spectra of what's contained. We also have this associated, the light that's given off. This is also associated with flame test, where we get different colors of light when the electrons move back down to the ground state. And this is also associated with fireworks, because the different colored light can be given off and depending on which salts you use within the fireworks. We also, in our class, we wore the spectral glasses to look at the gas tubes, and we were able to see the color of light in the gas tube, and in the spectral glasses you were able to see the different bright line spectra. I think we compared hydrogen and helium. The next question that was asked about was isotopes. Remember that isotopes are atoms of the same element, which means they have the same numbers of protons, because remember, atomic number or number of protons identifies an element. If you change the number of protons, you change which element you have. We also have different numbers of neutrons when we have isotopes, so that gives us a different mass number. So for example, we might have lithium 6, lithium 7, or lithium 8. These are 3 different isotopes of lithium. They have the same atomic number, which means they have the same number of protons, but they're different numbers of neutrons. Here we have 1, 2, 3 neutrons versus 1, 2, 3, 4 neutrons versus 1, 2, 3, 4, 5 neutrons. The different numbers of neutrons make them isotopes of each other. And since they're isotopes of each other, they have the same number of protons, but different numbers of neutrons. And again, remember, we can take the mass number and subtract the atomic number to get the number of neutrons. So this, we could also get that there were 4 neutrons by subtracting. I'm sorry, can't do subtraction apparently. We could get that there were 3 neutrons by subtracting. Here there's 4 neutrons, and here 5 neutrons. So isotopes, atoms of the same element, same number of protons, different number of neutrons, which gives them a different mass number. We talk about electron configuration. Electron configuration is found on the periodic table underneath the element symbol. So these are just pieces of the periodic table that you will get on the day of the Regents. And for example, 2892 for scandium means that scandium has 2 electrons in the first energy level, 8 electrons in the second energy level, 9 electrons in the third energy level, and 2 electrons in the outer shell, which is known as the valence shell, which means that if we wanted to draw or write scandium's electron dot diagram, we would do the symbol with 2 dots. Radium, on the other hand, starts off with this dash. I want you to note that at the bottom of the periodic table, it says that at any element starting at 72 really has 2,8 in front of the electron configuration. None of the electron configurations are going to start at 18. They always start at 2,8. So radium's full electron configuration is 2-8-18-32-18-8-2. It's actually longer than it looks. They just wouldn't fit on the periodic table that we have. So that means that radium has 1, 2, 3, 4, 5, 6, 7 shells of electrons. Its valence electrons, its 2 valence electrons are in the 7th energy level or the 7th shell. So radium actually has the same number of dots in its dot diagram because they each have 2 valence electrons, and that would mean that we would draw the dot diagrams the same way with just different symbols in them. But remember that for any element that's after or starting at number 72, this 2,8 is really at the beginning of the configuration. When we talk about nuclear chemistry, the questions that were submitted had to do with nuclear equations. Sorry about the poor copy of this. I just wanted to make sure that we could look at a couple of equations together. They didn't copy as well on the big screen. Hopefully you can see them. So when we have our nuclear equations, the first thing is that our nuclear reaction gives off a tremendous amount of energy. And that's because in all nuclear reactions, a small amount of mass is converted into energy. And when you have a small amount of mass converted into energy, it actually converts into a huge amount of energy. So all nuclear reactions give off way more energy than chemical reactions because of this mass to energy conversion. Now, when we look at nuclear equations, we have a nuclear reaction or nuclear equation type called transmutation. And And transmutation, remember, is when we have an atom of one element turning into an atom of a different element. So we actually change the elements present by changing the nucleus. The reason this is called nuclear chemistry is because it involves changes in the nucleus. If we change which atom we have, we change which element it is based on, then we have a transmutation. So all of the reactions up on the screen right now are transmutation because I have uranium, krypton, barium. Hydrogen here, helium here. Nitrogen and helium, oxygen and hydrogen. Radium, radon, helium. So different symbols on each side of the arrow means that we have transmutation. Now there are two main types of transmutation. We have natural and artificial. Natural transmutation happens on its own, where we have just one atom before the arrow. Artificial transmutation always needs to be bombarded. So the atom is not radioactive on its own in this way, but if we hit it with something or bombard it with something, its nucleus will react in the way that it's written. So natural transmutation has one species before the arrow, one nuclide before the arrow. Artificial transmutation will have multiples. Now, among the artificial transmutations, we have a couple of specific types. So here, this one here, specifically is called fission. Usually, I don't know if you can see, but this says 2, 3, 5. That's a really big mass number. You'll have a neutron bombarding something with a really big mass number, and it will break into two smaller pieces with more neutrons. So fission, you'll have something with a really large atomic number before the arrow hitting into a neutron, two smaller pieces, and more neutrons. The I in fission and the I in split go together. Then we have fusion, and the U in fusion for me is for unite, and it's usually hydrogen plus hydrogen making helium. Sometimes there's also neutrons in the products. So fusion is hydrogen plus hydrogen making helium. And again, usually we also, sometimes we also have a neutron in the products. For fusion, this happens on the sun, and it takes a tremendous amount of energy because we are combining two nuclei with like charges. Anything with like charges they're going to repel each other. Remember, the nucleus is positive. Two positive things will repel each other. So fusion requires a tremendous amount of heat and pressure to have it happen. And again, fusion happens on the sun. We do have this tremendous amount of heat and pressure available on the sun to drive the fusion. The next thing that was asked about was half-life. Remember that half-life is the amount of time it takes for half of a radioactive sample to decay into more stable products. We have on table N, we have our half-life time and our decay mode for multiple different nuclides, multiple different nuclear isotopes, or radioactive isotopes, I should say. Anything that undergoes a half-life is naturally radioactive, meaning that these substances will decay on their own without being bombarded. For example, every time a half-life goes by, the amount remaining will divide in half. So after one half-life period, 10 grams of carbon-14 is what we started with. At the end of one half-life period, we will have 5 grams of carbon-14 remaining. The other 5 grams will have decayed into more stable products. If a second half-life period goes by, that 5 grams of carbon-14 will now decay into 2.5 grams. 2.5 grams will be remaining. Another 2.5 grams will turn into something else through the radioactive decay. If a third half-life period goes by, we go down to 1.25 grams. If a fourth half-life goes by, we will go down to even half of that. If we're talking about percentages, we start with 100% at the beginning, 50% after one half-life, 25% after two half-life periods, 12.5% after 3 half-life periods, and it will just keep decaying and decaying. In class, we did the arrow method, where we started with a certain amount. After 1 half-life period, that amount divides in half. After 2 half-life periods, divides in half again, and it just keeps dividing in half and dividing in half and dividing in half each time a half-life period goes by. When we talk about periodic table, the first thing that we're going to go over is just the general trends. When we talk about the trends, remember that we can find a lot of these values on table S, so perhaps you want to take a little gander or take a little look at table S right now. Hopefully you took a little look at table S while I just had a little drink of water. When we talk about table S, when we talk about those trends, ionization energy is going to increase across a period and increase towards the top, and so is electronegativity. Electronegativity follows the similar trend, and we have fluorine here. We have francium here. Remember that as we get closer to fluorine, we get more like a nonmetal. As we get closer to francium, we get more like a metal. So non-metallic character increases closer to fluorine. Metallic character increases closer to francium. And remember, we're going to call francium the biggest loser. And that's actually going to mean that fluorine is the smallest gainer. And if we remember biggest loser for francium, and remember that fluorine is the opposite, francium is the biggest loser, that means that atomic radius is really big over here, atomic radius is small here. Francium loses electrons very easily. That means low ionization energy and low electronegativity. So we have low electronegativity, big radius, low ionization energy. Here we have small radius, high electronegativity, high ionization energy here. And if we go up, we get more like fluorine. If we go down, we get more like francium. If we go right, we get more like fluorine. If we go down, we get more like francium. And now the reasons that everything happens, as you go across a period, we are increasing the nuclear charge. Remember, the nuclear charge is based on the positive number of protons. If we have more positive protons pulling in the valence electrons, the atom will get smaller. If we have more positive protons pulling in the valence electrons, they will be held more tightly, higher electronegativity, higher ionization energy. But as we go down a group, the reasons why we see the trends that we do is because we are increasing the number of shells of electrons. Every time we add a shell on the outside, that just makes the atom get larger because we're adding more to the outside. But it also makes it harder for the nucleus to hold on to the valence electrons because these extra shells in the middle, in between, shield the valence electrons from the pull of the nucleus. So as you go down a group, having these extra shells makes it harder for the nucleus to hold onto the valence electrons because there's things getting in the way. We call that the shielding effect. So across a period, increasing nuclear charge, more protons pulls in the valence electrons tighter. Down a group, increasing number of shells, they shield the valence electrons from the pull of the nucleus. When we talk about bonding, remember, if you want to use this to remember, TICS, transfer ionic, covalent share. Say that again, TICS, TICS, transfer ionic, covalent share. Covalent substances that share electrons, they make molecules. So covalent makes molecules. You only have a molecular substance if you have covalent bonding. When we make molecules or talk about covalent substances, where they are soft They are poor conductors and they have low melting points. Ionic bonding, again, is this transfer of electrons making ions. They are hard, they have high melting point, and they conduct in liquid and solution only because that's when the ions can move. Remember, we need mobile charged particles in order to conduct electricity. Metallic substances have metallic bonding. It would just be a single metal, like if just the symbol Ag. They're usually solids, except for mercury, which is a liquid, and metallic substances are considered to be positive ions immersed in a sea of mobile electrons. They have such a weak hold on their valence electrons that they are able to move freely on them for the most part throughout the sample. Metals, things with metallic bonds, are shiny, which means they have luster. They're malleable and ductile, which means they're moldable and can be drawn into thin wires, and they're good conductors of electricity. Metals conduct electricity in every phase because of their mobile electrons. So keep in mind that ionic substances conduct in liquid and solution when their ions can move. Metallic substances conduct in every phase, solid, liquid, because of their mobile electrons. Covalent dot diagrams at this point, with the Regents just being a couple of days away. If you're watching this now, I'm not going to teach how to do dot diagrams. I'm just going to suggest that the ones that are on the screen for covalent and ionic, well, for covalent anyway, that you just take note of and just try to practice. They're on my review sheets as well. For covalent dot diagrams, they love to ask about nitrogen's triple bond. It's also considered a nonpolar covalent bonds. It's a nonpolar covalent bond because the two atoms of nitrogen have an equal claim to the electron, so they share them equally. They pull equally with having the same electronegativity, whereas carbon to oxygen or hydrogen to oxygen, those two bonds are called polar covalent bonds because they are between atoms of different nonmetals. So they have different claim or different pull on the electrons based on their differing electronegativities. Remember, I used the example of my sister and I sharing a car. She's older, so she has more pull. When we were younger and sharing a car, I really didn't get to take the car very much at all, but according to my parents, we were sharing. So the higher electronegativity will be the one that pulls harder on the electrons, and we'll get the the negative side if the molecule is an asymmetrical polar molecule. So remember, also for covalent dot diagrams, CO2 and N2 are symmetrical nonpolar, whereas water is asymmetrical polar. Oxygen has a higher electronegativity, so the valence electrons are pulled more tightly by the oxygen and less tightly by the hydrogen, which gives it a positive side and a negative side. So this is a polar covalent bond that also makes an asymmetrical polar molecule because it has a positive side and a negative side. Here we have a polar covalent bond, unequal sharing, but we have a symmetrical nonpolar molecule because of the fact that even though oxygen pulls more tightly, it's pulling more tightly on each end. There's not just one side that's positive and one side that's negative. For the nitrogen, we have a nonpolar covalent bond as well as a symmetrical nonpolar molecule, again, because of the equal or symmetrical distribution of charge. Polarity and like dissolves like. Again, for molecules, we said M-SNAP. For molecules, symmetrical is nonpolar, asymmetrical is polar. Symmetrical nonpolars tend to dissolve in each other. Asymmetrical polars tend to dissolve in each other. And remember that polar bears swim in water. Water is polar. So only polar substances tend to dissolve in water because water is polar. If something dissolves in water, we will say it's polar. If something does not dissolve in water, we will infer that it is nonpolar. The intermolecular forces and the polarity base, all molecules have dispersion forces, whether they are polar or nonpolar, but it's a weak force based on temporary movement of electrons. Whereas polar molecules, ones that have a negative side and a positive side based on the shape of being asymmetrical polar. These molecules will have what are called dipole-dipole interactions, where the negative side of one molecule can attract the positive side of a neighboring molecule. This is a stronger intermolecular force than the dispersion forces because this is what's called a permanent dipole. That positive and negative charge exists all the time, so those attractions can be stronger. And then finally, hydrogen bonding is even stronger if you're talking about among similar types of molecules. When we have FO or N bonded to H, the intermolecular force between molecules can also be hydrogen bonding, and hydrogen bonding is a stronger special type of dipole-dipole force. So hydrogen bonding is sort of like a subset of dipole-dipole, but it's stronger than a dipole-dipole, which accounts, this color may not be coming up so well on my screen, accounts for the higher than expected boiling point for H2O. They love to ask about that higher than expected boiling point for water, and it's because water has hydrogen bonding in addition to its dispersion forces and dipole-dipole forces. We can also talk about the fact that, remember, boiling point is directly related to the strength of intermolecular forces, regardless of the type. So if you have something with a higher boiling point, that means that it has stronger intermolecular forces. If something has a lower boiling point, that would mean comparatively its intermolecular forces are weaker. We talk about ionic dot diagrams. We did go through a whole process to make sure that we knew why and where these electrons were coming from. But basically, when you do ionic dot diagrams for the final answer, you're going to take the metal in brackets with no dots, and you're going to take the charge, that's the oxidation number on the periodic table. Your nonmetal will have 8 dots, will also have its negative charge from the periodic table. If those charges are equal and opposite sign, then that's the end of your dot diagram. So again, metal, no dots, positive charge from the table, non-metal, 8 dots, negative charge from the periodic table, equal and opposite, we're done. If you do that, where the charge of the metal and the charge of the nonmetal are different, you can do one of two things. You can go and say, okay, well, when I crisscross and drop the signs, I get CaCl2, so I can then just draw 2 Cls and 1 calcium. Or if you don't want to have to draw another thing, you don't have to draw the second one, you can just put a coefficient of 2 in front of the nonmetal there. Whatever number is down here can just become the coefficient of the bracket. That's up to you. So again, you can either draw it twice or put in a coefficient in front of the one that gets a subscript in the crisscross formula. For the moles and stoichiometry chapter, when we were talking about significant figures, again, this generally does not show up that much anymore on the Regents exam. But again, we use Pacific Atlantic for decimal present and decimal absent. For Pacific, for decimal present, the zeros on the Pacific Ocean side are the ones that are not significant figures. Everything else, starting at the first number on the Pacific side, that's not a 0, towards the land, these would all be significant figures. So 1, 2, 3, 4, 5, 6, 7. This has 7 significant figures if you wanted to count them. There are no zeros on the Pacific side here. So this whole value here is considered significant figures. 1, 2, 3, 4, 5, 6. Here we have zeros on the Pacific side. Everything else towards the land, starting at the first number that's not a 0, is a significant figure. So this one has 3 significant figures. For decimal absent, that means there's no decimal anywhere. it's the zeros that are in the Atlantic Ocean that are not part of the significant figures. Remember, these zeros are still needed for placeholder reasons. We can't change the magnitude or the size of the number, so we need those zeros to hold the place. They are just not part of the exactness of the measurement. So that means that these are my significant figures. Zeros in the Atlantic Ocean, not significant figures. Everything starting at the first non-zero inland towards the land is a significant figure, and this one doesn't have any zeros at all. So this has 4 significant figures. Again, it's only zeros that could possibly not be significant figures. Anything that's a 1, 2, 3, 4, 5, 6, 7, 8, or 9 is automatically a significant figure. So it's just figuring out which zeros aren't part of the significant figures of the measurement. When we talk about gram formula mass and finding gram formula mass, we also call that the GFM. Remember that there is a formula on table T regarding number of moles equals given mass over the gram formula mass if you needed to do a mole calculation. If we want to find the gram formula mass of C6H12O6, we are going to take the mass from the table of carbon and multiply it by 6. Now, I always do to the 10th, and I always tell you to do to the 10th in my classes. If it's a multiple choice question and the answers are all rounded to the nearest whole number, you can certainly round to the nearest whole number when you're doing your calculations. But I usually just default to going to the 10th. So carbon times 6, 72.0. Hydrogen's number on the periodic table times 12. Oxygen's number on the periodic table times 6. I add them all up. That number of grams is the gram formula mass, and that would also be the mass of 1 mole of glucose. If we're talking about percent composition, we could take that same gram formula mass. Remember, percent composition by mass is on the table T, and it's the mass of the part over the mass of the whole multiplied by 100. That percent composition by mass, if you wanted to do it from the gram formula mass, if you want a percent of carbon, you would take carbon's total mass when you multiply it out by the 6, divided by the gram formula mass of the compound, and then multiply by 100. Sorry, I thought the answer was on here. And then if you wanted the numerical setup, this would be what's called that numerical setup. And then you could just do the math on your calculator if they asked you for the actual answer. Just give me 1 second. Okay, next thing that was asked about was balancing equations. And remember that for balancing equations and any equation that's written in chemistry, this arrow can actually be thought of as an equal sign. Everything before the arrow should be equal to everything after the arrow. And if it's not, then we don't have a balanced equation. So for balancing equations, we want to make sure that we have the same number of moles of atoms on each side of the arrow. So having the same number of moles of atoms on each side of the arrow means that we are in accordance with the law of conservation of matter. Remember that all chemical equations and all nuclear equations and all equations in general, all reactions, all chemical reactions, all nuclear reactions, all reactions in general they follow the laws of conservation, conservation of matter, conservation of energy, all that. We conserve mass, energy, and charge in all reactions. And the first step is going to be making sure that we have the same number of atoms on each side. So this equation is already balanced, but I'm just going to take you through the steps of starting it. So we would first take our numbers of carbons that are, it wasn't balanced in the beginning. We will take our number of carbons on each side, which in the beginning was 1 carbon on each side. We had H4, this one we started out with H2, and we start out with 2 O's on this side, and we start out actually with 3 O's on that side before we put in the coefficients. I usually suggest that you balance your carbons first your hydrogens second and your oxygens last. So since the carbons were already balanced, the next thing to do is to get the hydrogens balanced. So we have H4 on this side. Putting a 2 in front here makes 2 times 2 makes H4 on that side also. Once that happens, this 2 oxygens plus this 2 times 1 makes 4 oxygens. And in order to finish the balancing, we need to get 4 oxygens on the right-hand side of the arrow as well. If we put a 2 in front of the O2, that is going to make sure that we have the same number of oxygens on each side as well. So I can go in and change this 2 to a 4, and now we have 1 mole of carbon atoms on each side. We have 4 moles of hydrogen atoms on each side, 4 moles of oxygen atoms on each side. Remember, we can only put in coefficients, these numbers in the front, and then the coefficients multiply by everything in the formula. They multiply by the subscripts at the bottom, and we're doing it like a puzzle in order to get the same number of moles of atoms on each side. For the reaction of the chapter for solutions, molarity was a question that people asked. Remember, there's 2 ways that we can do concentration. We have molarity and we have parts per million. So first, if they asked a question about what is the molarity, they could also say what is the concentration. And then that would give you a clue to look at table T and look at the concentration section on table T, and then they say, okay, well, we have a certain number of moles and a certain number of liters. Oh, I'm going to use this concentration formula because it says moles and liters. We're going to take the formula. Remember that we can abbreviate the formula. Molarity is big M, the abbreviation for moles is MOL, and the abbreviation for liters is L. And when we put that information in, we put the moles over the liters and we divide out, we get our answer of 0.094 molar NaCl. That means that it is 0.094 moles per liter. So again, if you needed the numerical setup, you would stop here. A numerical setup needs to be just the numbers. You don't need the units for the numerical setup, just so that someone could take their calculator and get the answer with it. For parts per million, that's the other concentration. If they give you a certain number of grams of a substance and a certain number of grams of water, and we want to find the concentration in parts per million, it's just like percent, but we're going to do part over whole times 1 million. So the solution is going to be the AgCl plus the water. So here we have to do the total as 100.008 because they gave them to us separately. If it says 0.008 grams of AgCl in 100 grams of solution, then that's going to be a different story. So now we have the 100.008 that should have been divided by 100.008, and we get, it would round out to 80 parts per million anyway. But again, this part here would be my numerical setup. I would be able to take the calculator and find the answer with just the calculator. But then if they ask for the actual answer, you're going to actually divide and multiply and calculate. The question about electrolytes that was asked, remember that an electrolyte is something that dissolves in water to produce a solution that can conduct electricity. Remember that acids, just put it on the other side, remember that acids, bases, and ionics are all considered to be electrolytes. They're considered to be electrolytes because when they dissolve in water, they make mobile ions, and electrolytes are things with mobile ions in solution. They will allow the light bulb to light because as the current, where the electrical current comes in here and goes into the solution, even though this wire is cut, remember the current can be transmitted because of these mobile charged particles, and then it will light the light bulb. Sugar does not conduct electricity because it is has covalent bonds. Covalent bonds make molecular substances. Remember, splash. Molecular substances are soft, poor conductors, low melting point. Water is also molecular. It has covalent bonds. Okay, so it does not have mobile ions in the solution, or it doesn't have mobile ions to conduct electricity. Table F is the solubility table. Remember that you're going to look for the formula. You look for a piece of the formula here and a piece of the formula here. You will start in the first column of each side. And if you find just something in the first column, it is the heading at the top. If you find that the formula has something in the first column and something in the second column, you negate what's at the top of the column. Excuse me. For acids and bases, remember that we have table K and table L. Table K is some common acids. Table L is common bases. If we're talking about the Arrhenius theory, acids have H plus as the only positive ion in solution, which is hydrogen ion, and bases have OH minus or hydroxide as the only negative ion in solution. Remember that acids are sour, they're not slippery, they have a pH of less than 7, they make H plus ions in aqueous solution, they corrode metals. Remember they react with metals high on table J. Has to be above hydrogen on table J to react and produce hydrogen gas. And they're going to turn litmus red. And we also had to know phenolphthalein, colorless. For bases, they're slippery. They have a pH of over 7. They're bitter. They make hydroxide ions in solution. They don't corrode metals. They don't react with metals to make hydrogen gas. They turn litmus blue. And phenolphthalein, that dark pink color. Remember that bases are usually a metal in front of OH, and acids usually start with H or end in COOH. When we talked about the alternate theory, or sometimes they say one acid-base theory, I don't know why they think that you can't remember Bronsted-Lowry. Remember it's H plus, turn blue, H plus bad. For this other theory, H plus, bases accept, acids donate. Talk about the pH scale. Remember, it's a logarithmic scale. Remember, pH is negative log of H plus. Every number on the pH scale is a 10-fold change in H plus or OH minus. Remember that at neutral, the concentration of H plus is equal to the concentration of OH minus because they're always both there. And as we go higher on, or lower here, as we go lower on the pH scale, closer to 0, we get more acidic. As we go lower on the pH scale, we increase the amount or concentration of H plus while decreasing the concentration of OH minus. As we get closer to 14, we get more like a base. Remember, basic does not mean simple in chemistry. Basic means more like a base. And we are going to increase the hydroxide while decreasing the hydrogen. From a pH of 1 to 0, we are multiplying the hydrogen by 10 and dividing the hydroxide by 10. From 2 to 0, it's a 100-fold change. From 3 to 0, it's a 1,000-fold change. Remember that the amount of places you go on the pH scale is actually the amount of zeros. So 1 place is 10, 2 places is 100, 3 places would be 1,000 times. Acid-base neutralization reactions happen when acids and bases react with each other. We're always going to form salt and water. I don't know why this says salt and this says water. But remember, salt is not just table salt. Salt could be any ionic compound that's not an acid and not a base. And the way that we do this, we switch our inners and our outers. So H is the outside, goes with OH. K goes with the Cl. And to get the formula of the salt, you're going to look up the oxidation numbers and crisscross and drop the signs. Remember, if these charges are equal and opposite, they cancel out. If they're not, we're going to have subscripts in the formula. Whenever you have subscripts in the formula, remember that's when you're going to need to go ahead and balance. If the subscripts cancel out and it's just KCl or just NaCl, you're not going to have to go back and balance. Water is always a product between the H and the OH. The front of the base and the end of the acid always go together to make the salt. When we talk about kinetics, and actually, let me go back to acids and bases for a second. The other thing that if they say the word neutralization, you also might need to use the titration formula, which is MAVA equals MBVB. That titration formula is on table T. And remember, we take the concentration of the acid times the volume of the acid and set it equal to the concentration of the base times the volume of the base so that we can find the concentration of an unknown acid or base or find out how much acid or base to use to neutralize the other. For kinetics and equilibrium, the first question that was asked about was about the potential energy diagrams. I'm just going to take a little second here. Hold on one second. So talking about these potential energy diagrams, remember the same thing holds true as did with the heating and cooling curves. If we have something going uphill, it's endothermic. Downhill is exothermic. Remember that we are measuring the potential energy over a certain amount of time. So the bottom's either going to say reaction pathway, reaction coordinate, time, something like that. Remember that we're going to have three values that hit this x-axis here, and they're going to hit places on the graph. So if I put in something that goes from the x-axis to the reactants, that would be the PE of the reactants. X-axis up to the products would be the potential energy of the products. X-axis up to the activated complex would be the potential energy of the activated complex. The amount of energy it takes to push the reactants to the top is the activation energy for the forward. The amount of energy it takes to push the products to the top would be the activation energy of the reverse. Remember that if we add a catalyst, we change the reaction pathway, lowering the activation energy. So the reactants have to stay the same, products have to stay the same, but this hill will change and get lower if we add a catalyst. Adding a catalyst will speed up both reactions by the same amount. So adding a catalyst will not shift the equilibrium, but it will speed up both reactions forward and reverse. We also have this value that I'm going to erase all of this. So you can always pause and go back if you need to see this again. There is rewind available if you're watching this live. But if we go back, remember also that I told you you can look at the potential energy diagram like a hamburger, and you can say, okay, we have our bun on the top here. My dashed lines. We have a bun on the top. We have our bun on the bottom. And in the middle here, this is our delta. I don't know why my color is changing, but this is our delta hamburger. So our delta hamburger, anywhere in this area, we can put the delta H. So we can slide it in here, anywhere in this hamburger. So if you picture every potential energy diagram as a hamburger, the top section is going to be a bun, the bottom section is a bun. We're trying to locate the the delta H, and that's always in the hamburger. The potential energy diagram of the exothermic graph will actually look the same. Anything x-axis to the reactants is potential energy of the reactants. X-axis to the products is potential energy of the products. X-axis to the activated complex, potential energy of the activated complex. Reactants to the top, forward activation energy. Products to the top, reverse activation energy. Delta hamburger, anywhere in that section. Remembered something. Okay, when we talk about this also, remember that if this one is endothermic, delta H is equal to the products minus reactants potential energy. So for endothermic, it has a positive value of delta H. And for exothermic, it has a negative value for delta H. For endothermic, we would have reactants plus energy makes products. For exothermic, we would have reactants make products plus energy. The 5 factors that affect the rate of a chemical reaction are temperature, concentration, surface area, catalyst, and nature. Remember that increasing temperature, concentration, and surface area, if we increase these, we increase the rate of a chemical reaction because we increase the number of effective collisions. Remember that based on collision theory, reacting molecules must hit or collide with each other. They must have enough energy, and they must hit in the right spot, which they call proper orientation, in order to lead to a reaction. So increasing concentration, temperature, and surface area leads to more effective collisions, making the reaction go faster. Adding a catalyst changes the pathway or series of steps that the reaction takes. Changing the pathway also lowers the activation energy. Lowering the activation energy makes the reaction go faster. Nature, on the other hand, is not something that you can change. Some reactants and products, some reactions are faster just based on what is reacting, and some are slower based on what's reacting. So the fastest reactions would be ionic solutions because they have very low activation energy because the ions separate in solution, whereas the slowest would be organic reactions. Organic reactions have high activation energy that makes them very slow. That's why many organic reactions require catalysts. That's why we have enzymes in our body, because the reactions in our body would happen very slowly, too slow to keep us alive without those activation energy helpers. Reversible reactions can reach equilibrium. Equilibrium condition is when we have equal rates of the forward and reverse. Spell, that would be good. And constant concentrations of the products and the reactants. So these two things cannot be confused with each other. It's not constant rates, it's equal rates, constant concentrations. Once we've reached equilibrium, the concentration of reactants and products stops changing. Le Chatelier's principle tells us that we use add away, take toward, increasing pressure shifts to the side with less moles of gas. Add away means that if we add something, remember I always tell you that we want to put the line through the arrow and identify your left and your right. If you write it on the page, it's much easier to make sure you don't make a mistake. If we add nitrogen, nitrogen is on the left. If we add nitrogen, that means we'll shift to the right. That means we'll increase what's on the right, and we will decrease what's left besides what we changed on the left. Shifting to the right means that we are going temporarily quicker to the right-hand side or in the forward direction. It means we're building up products faster than the reactants are being built back up. Take towards means if you remove something. If I remove hydrogen, hydrogen is on the left. Moving something from the left means that we also, I don't know why my pen is changing color, means that we also shift left. Shifting to the left means we increase what's on the left while decreasing what's on the right. Whatever side you shift towards, that stuff increases. Whatever side you shift away from, that stuff decreases in concentration and number of moles. If we increase pressure, we shift to the side with less gas. So we're going to have to add up the coefficients. So I have a 1 and a 3 in front of my G's here. That makes 4 moles of gas on the left. I have a 2 here. That makes 2 moles of gas on the right. Remember, you're only looking at the coefficients for the things with G's. So less gas would be on the right. So if I increase pressure, I shift to the right. That means I increase the amount of ammonia and I decrease the amount of nitrogen and hydrogen. Shifting to the right means increasing what's on the right while decreasing what's not on the right. We talk about redox. Redox for half reactions and balancing. The first step is going to be to put in your oxidation numbers. Remember, elements by themselves have an oxidation number of 0. For ionic compounds in redox reactions, the nonmetal is going to get its negative charge from the periodic table, and then the metal will get a positive charge that makes it add up to 0. So -1 times 2 is a total charge of -2. That means the copper has to be a +2. Same thing for the zinc over there. My chlorine here is a spectator ion. It's not part of the redox reaction. If I want to do my half reactions, remember I say Ger, down, Leo, up. Gaining electrons is reduction and the charge goes down. Ger goes first because electrons go before the arrow in reduction. Losing electrons is oxidation and the charge goes up. Leo goes second because the electrons go after the arrow for losing electrons. Zn0 is turning into Zn plus 2. Cu plus 2 is turning into Cu 0. Charge going up for zinc. That makes zinc 0, the species that is oxidized. Charge going down for copper plus 2. That makes copper plus 2 the species that is reduced. Since the electrons go after the arrow for oxidation, I put them after the arrow for the zinc. I subtract the charges and multiply by a coefficient if there is one here to get the number in front of the electrons. Subtract the charges, multiply a coefficient if there's one there to get the number in front of the electrons. Then if the electrons are the same, we are balanced. If they're not the same, you wind up multiplying your half reaction by a coefficient. Remember, we put them in parentheses and we multiplied out. So if we needed to get the electrons the same, we'd put something here and something here to multiply the whole half reaction by something to get the electrons to be equal. Voltaic and electrolytic cells. Voltaic is also called a galvanic cell. Remember that a voltaic cell is a spontaneous redox reaction where chemical energy is converted to electrical energy. We have to have an anode and a cathode. We said that we have anox and big red cat that actually go for both voltaic and electrolytic. The anode is always the site of oxidation. The cathode is always the site of reduction, and the cathode always gets bigger. Electrons flow through the wire from anode to cathode. Ions flow in the salt bridge. Ions go in the salt bridge in order to make sure that the solutions do not become charged, make sure the solutions stay neutral. And remember, eventually the voltmeter will read 0. That's when that's when the reaction has reached equilibrium. The electrons go from anode to cathode through the wire. The cathode gets bigger because ions make atoms. The anode gets smaller because atoms that are part of the anode become ions, and those ions go into the solution. So ions are turning into atoms at the cathode, atoms are turning into ions at the anode. So the anode is getting smaller and the cathode is getting bigger. A voltaic or galvanic cell is a battery. So we use this chemical reaction to provide us with electricity to power your phone or some other device that needs a battery, your flashlight, something like that. Whereas a battery is needed for an electrolytic cell, which this specific type of electrolytic cell is electroplating. And the battery is necessary to start the non-spontaneous redox reaction. So where in the voltaic cell, it's a spontaneous reaction where the electrons just move on their own based on what's called the electromotive force. In a setup for electroplating or any electrolytic cell, we use a battery to force the electrons to move. We are actually converting electrical energy to chemical energy in an electrolytic cell. For electroplating, the same metal is first oxidized at the anode and then reduced at the cathode. We still use anox and we still use big red cat, but we're oxidizing and reducing the same metal. So basically the ions go through the solution, the electrons go through the wire, and they meet up on the surface of the object, making a coating, a permanent coating on that object. The object, the spoon, the fork, the necklace is always the cathode. The solid piece of metal, the desirable metal to be plated, is always the anode. Again, we always have the same metal oxidized at the anode and then reduced at the cathode. We also have, for an electrolytic cell, recharging a battery. As soon as you plug your phone into the charger, that's also an electrolytic reaction. You're adding electricity from the charger to the battery in order to allow it to kind of get its electrons back where they started so that we can have that process, that natural process, work again. We talk about organic chemistry. Remember about table P and Q? Remember I call table P table prefix? The table P is going to tell us how many carbon atoms are in a molecule based on the prefix. Remember we did metheth, propene, pentex, heptacnon, dec for our prefix quiz. So you're going to have something like methane, ethane, propane, butane. You're going to have all of these different all these different prefixes go into the formula names, into the compound names. Remember we had alkanes, alkenes, and alkynes. Alkanes, alkenes, and alkynes are, if we put them in alphabetical order, we can name them 1, 2, and 3. Alkanes always have single bonds. Alkenes have 1 double bond. Alkynes have 1 triple bond. For alkanes, it's always more than double the number of carbons to get the hydrogens. For alkenes, it's always exactly double the number of carbons to get the hydrogens. I call that one double-double. If there is double the number of carbons to get the hydrogens, there is a double bond somewhere. And for alkynes, it's less than double the number of carbons to get the hydrogens. Remember that alkanes, out of all of these, are the only ones that are saturated. Saturated means it has all single bonds. So again, if we're talking about substitution and addition for types of organic chemical reactions, if something is saturated, it has only single bonds, will undergo substitution, and substitution has 2 products. When we start with all single bonds, there's no place for these atoms to just join the molecule. we have to kick a hydrogen out in order to get one of these chlorines in, and it can only happen one at a time. So one of the chlorines is going to switch places or substitute itself for one of the hydrogens. And now after that, the chlorine is in the molecule, the hydrogen is out. Whereas for addition, always starts with a double or triple bond, and addition has a product. Usually you'll see addition with a double bond. That double bond will turn into a single bond. When that double bond turns into a single bond, it opens up a spot on each hydrogen where they can pick up a new atom. So for addition, we only have one product because both of these chlorines can join on to the two separate carbons once that double bond becomes a single bond. For fermentation and saponification, remember the basic thing to remember is that for fermentation, we are making alcohol and bubbles. It is the sugar that is the food or the metabolic requirement for yeast, and the yeast uses the sugar in its own life processes in order to get its energy. When it does this, or in order to make the energy sort of into a more usable form, in order to produce its ATP, when it does this, its byproducts or its waste products are alcohol and carbon dioxide. So you're going to see sugar, you might see yeast zymase or the word enzyme, and we're making alcohol and carbon dioxide. For saponification, remember that the first four letters in saponification can be rearranged to make the word soap. You're going to have fat plus base. A lot of times they'll use the word hydrolysis of fat plus base. I'll say hydrolysis of a fat and base, and you'll make soap and glycerol. For combustion, remember, is always combining with oxygen. Combustion is burning. And we always, for organic combustion, make carbon dioxide and water. And if you could please look at the top 5 or 6 reactions on table I, you'll see those are all combustion reactions where oxygen is a reactant, carbon dioxide and water are products. And you'll see that they are all exothermic. They are exothermic, which means they give off energy, which makes sense. We use propane in our many barbecue grills. We combust it or burn it to give the heat to cook our food. Methane is used in natural gas in your house. If you have natural gas, we burn it in your heating system to give off the heat to heat your house. Exothermic gives off heat. Whereas esterification, we said we had kooky and ester because an ester will have COOC in its formula. And for esterification, it's an acid plus an alcohol, making an ester and water. Because if we look at the acid, the OH comes off. Sorry, no, it doesn't. If we look at the alcohol, the OH comes off. The H comes off the acid. These guys go together to make the water. And then this molecule right here can just slide right there, and we wind up with the COOC. So this would be propanol, makes the propyl, ethanoic acid makes the ethanoate. Finally, polymerization. I think this is my last slide for the live stream here. Finally, polymerization, we take lots of separate molecules. Wow, that shouldn't be like that. That shouldn't be there. We take lots of separate molecules. The coefficient means that they are not connected. And then when they are bonded or connected, we have this subscript. So the coefficient in the front means that they are separate. The subscript means that they are connected, and we are going to take many small pieces and put them together in polymerization. Remember, poly means many. We're taking many monomers and connecting them for polymerization. You'll usually see it like this. An N in front an N at the end, and they'll say that that N is somewhere around the order of 2000. So polymerization, remember we made slime, we said that rubber is a polymer, we said that cellulose and starch are polymers. You know, we said that plastic is different plastics are different polymers, and they have many uses, but it's lots of molecules connected. This was the live stream for Mrs. T's Regents Review. Mrs. T's Chem Talk Regents Review. Hopefully this was helpful. Hopefully you got some information to help you study for your Regents. Don't forget to check out the other videos on my channel. I have lots of other Regents Review videos. In fact, at Regents Review time at the top of the channel, there is a Regents Review playlist. You can feel free to watch any of those videos for help studying. If you want to, you can also subscribe to the channel to make sure that you are up to date on any new videos that come out, or even just so that you can find it easily in your own YouTube. And I hope that everyone has a great day. I hope you have a good time studying and you do well on the Regents exam. Good luck.